Welcome to the Sleepy Brain Facts channel. Tonight, you embark on a journey into the great unknown, where we will delve into some of the most profound mysteries of our universe. Despite the incredible advancements science has made, a vast frontier of unanswered questions still awaits. You may have noticed how we have mapped galaxies, measured the distant glow of ancient light, and explored the behavior of particles far too small for the naked eye to perceive. Yet, with every discovery, you find that new layers of uncertainty emerge. The universe guards its secrets well, and many of the concepts we hold dear may simply be stepping stones towards something far grander. Consider this: space may be stranger than our models suggest. Time might not behave as we expect, and even the very foundations of matter and energy could be mere fragments of a much larger theory. If you find comfort in these tranquil explorations, I warmly invite you to like, subscribe, or share your thoughts below. Each action helps others discover this space, one sleepy soul at a time. But for now, take a moment to relax, breathe deeply, allow the day to drift away, and let your mind gently settle into a state of calm. Let's begin. The universe may hold regions forever hidden from our sight. Beyond what we can observe, it expands into realms whose light will never grace our eyes. Those distant regions are not merely far away, they are separated by the finite speed of light and the relentless expansion of space. Even if you had the most advanced instruments and waited longer than any human lifetime, some aspects of reality would still remain inaccessible. In those unseen realms, matter could be organizing itself into galaxies and structures that never emit a single photon towards you. The laws of physics might adhere to the same principles you know, or they could bend in ways you cannot even begin to verify. When you gaze at the night sky, you are looking at a tiny fragment of a vast expanse. You realize that events are unfolding right now, yet no one here will ever witness them. The universe may be filled with stories that will remain untold for eternity. Entire regions of space could exist with entirely different laws of physics. Many contemporary theories suggest that what we consider the laws of nature may not be fixed and unique. Some concepts in cosmology and fundamental physics propose that constants, like particle masses and interaction strength, can vary in different areas of a broader reality. In one cosmic domain, stars might never ignite, while in another, atoms could be unstable, or entirely different forms of matter might emerge. Your understanding is limited to your own section of the universe, where the conditions happen to favor long-lived stars and complex chemistry. Imagine a vast horizon stretching beyond your current understanding, where the very concept of a stable atom might not exist. What if our familiar physics is just a local dialect in a much larger realm of possibilities? If that holds true, then what we consider fundamental might actually be akin to a regional custom, one among many, with no means to explore or compare them. You find yourself pondering the mystery of what transpired before the first moment of time. Our most advanced cosmological models explain how the universe evolved from a hot, dense state, yet they fail to clarify what, if anything, existed before that. At the dawn of time, both gravity and quantum physics play crucial roles. Still, we lack a unified theory that seamlessly integrates them. When you trace the equations backward, they eventually yield meaningless results, as if the very fabric of time itself reaches an end. Some theories propose a prior phase of contraction, while others envision a bounce, or even suggest that time emerges from something more fundamental, something that defies our conventional notions of before and after. As you gaze at the sky, the observations offer tantalizing hints about that early fireball, yet they cannot penetrate the veil shrouding what lies beyond. perhaps the question of a beginning itself is not the right approach to understanding this profound mystery. Your mind naturally wanders to profound questions. What does it mean for time to begin? Is there truly a reason for that very first moment? Space, in all its mystery, might be boundless, or perhaps it loops back on itself. When you gaze into the cosmos, you can observe how space curves on grand scales. Yet those observations do not fully reveal the overall shape of everything that exists. Consider this. One possibility suggests that space extends infinitely, stretching endlessly with no boundaries, never returning to its starting point. Alternatively, space might possess a finite volume akin to the surface of a sphere, but without edges. Imagine traveling far enough in one direction, only to eventually circle back to where you began. The various shapes of space could subtly influence the patterns of structures you see in the night sky. However, these differences are incredibly delicate and challenging to detect. So far, our observations align with numerous possibilities. The true shape of the universe could be simpler or even stranger than you can fathom. It's possible you may never journey far enough to uncover the truth. Moreover, there might be invisible dimensions woven intricately with the ones you experience. Your reality unfolds in 3 spatial directions and one of time, inviting you to explore the mysteries that lie beyond. Some theories aiming to unify the forces of nature suggest that additional spatial dimensions may exist. These extra dimensions might be curled up to sizes so small that we don't notice them in our daily lives. Their presence could subtly influence how particles move and how gravity behaves, leaving behind faint traces in experiments and cosmic observations. Imagine a scenario where every point in our familiar space is actually a tiny multidimensional structure with paths looping through directions that our senses cannot perceive. If these hidden dimensions exist, they could give rise to new kinds of particles or even connect distant regions of space in ways we have barely begun to imagine. Discovering these dimensions requires creative experiments and a thoughtful examination of how the universe has evolved. The notion that our world might just be a part of a larger dimensional tapestry is both open and profound. We often discuss space as if it were an empty stage, a smooth backdrop against which matter moves and light travels. However, we truly do not understand what space is made of. Is that stage fundamental, or is it constructed from something deeper? Some theories of quantum gravity propose that space might emerge from discrete building blocks, perhaps a network of relationships or tiny units of area and volume that appear continuous only from a distance. Imagine a universe where space emerges from intricate patterns of quantum information, forming a vast web of entanglement. This web gives rise to distance and geometry as collective effects. Even in the realm of ordinary physics, the vacuum is not genuinely empty. It brims with fluctuating fields that can spawn real particles. These insights hint that our idea of a simple void may be an illusion. If space possesses an underlying structure, then at incredibly small scales, our familiar notions of location and distance might dissolve. They could be replaced by concepts that challenge our usual understanding. Time, too, may flow differently in parts of the universe that remain out of reach for us. Relativity teaches us that the passage of time is not an absolute constant. It depends on motion and gravity. Clocks situated deep within gravitational wells tick more slowly than those positioned far away. Similarly, objects moving at high speeds experience less elapsed time compared to those at rest. Across the cosmos, matter organizes itself in complex patterns, ranging from dense clusters to vast empty regions. This means that the rate of time can vary significantly from one location to another. In distant galaxies, processes might unfold at a rhythm slightly different from our own, even if those there would not perceive this difference in their immediate experience. In extreme environments near very compact objects, these variations become even more pronounced, allowing outside observers to witness events unfold in what appears to be slow motion. As you reflect on these ideas, consider the profound implications they hold for our understanding of the universe and our place within it. You find yourself pondering the complexities of time and space. The challenge of synchronizing clocks across vast distances leaves you with a mosaic of local times, each shaped by its own context. The notion of a single universal now falters as you consider the cosmos. Imagine the universe as just one bubble in an ocean of countless others. Some theories of cosmic inflation propose that the universe's rapid expansion did not cease uniformly. In certain regions, this expansion may have slowed and cooled, creating bubbles where conditions are stable enough for galaxies and stars to form. Meanwhile, other areas may have continued to expand, generating new bubbles with unique characteristics. Your observable universe is merely one of these bubbles, nestled within a finite space amidst a much larger, inflating backdrop. Some bubbles may never interact with yours, remaining isolated by vast distances and areas where space stretches at an astonishing rate. In these distant realms, the laws of physics could differ, or perhaps resonate with your own in ways that remain forever elusive. This perspective transforms your understanding of the universe into just one example within a broader multiverse. While it provides insights into certain cosmic enigmas, it also prompts profound questions about the nature of reality itself. As you reflect on these ideas, you might find yourself captivated by the mysteries that lie just beyond your reach. Would you like to delve deeper into these cosmic wonders, or take a moment to rest and absorb this intriguing concept? Imagine a universe filled with structures that are beyond our current understanding. Astronomers have uncovered vast clusters, intricate filaments, and expansive sheets of galaxies that stretch across incredible distances, creating a cosmic web that binds the fabric of space. Yet, our observations are limited by the reach of light from the early universe and the specific areas of the sky we have meticulously studied. It's entirely possible that beyond what we can currently observe, there exist arrangements of matter that are even more magnificent than the largest structures we know today. These superstructures might challenge our existing theories about the cosmos. The universe, as we expect it to be, should exhibit uniformity. However, some intriguing patterns hint at deeper complexities, revealing alignments that seem more organized than conventional models would suggest. Are these anomalies mere coincidences, or do they hint at something more profound? The truth remains elusive. If there are indeed colossal structures lurking beyond our observational limits, their gravitational pull could subtly influence the motion of the galaxies we can see, leaving only faint traces of their existence. In this way, unseen forces might quietly shape the cosmos we can measure. As we reflect on the nature of the universe, we find ourselves pondering whether it has an edge or if it extends infinitely without boundaries. When we think of the universe, it's common to envision a vast expanse with some sort of border, beyond which lies emptiness. Yet, the reality may be far more complex than we can imagine. In the realm of physics, the concept of an edge to space presents a challenge. Edges typically suggest the existence of something beyond. One intriguing alternative posits that the universe is finite, yet curved in such a way that it possesses no boundaries, much like the surface of a sphere. This surface has a limited area, but does not truly end anywhere. Another perspective suggests that space extends infinitely, without edges or an exterior, merely offering more of the same fabric. Our observations of the cosmic background and the arrangement of galaxies provide insights into the geometry of the visible universe. However, they do not definitively resolve the larger question of the universe's overall structure. Our language often falters as we attempt to describe the entirety of existence from within its confines. Whether the universe has a genuine edge, a closed shape, or stretches infinitely, remains one of the most profound mysteries. Consider that the universe might be expanding into realms beyond our perception. When we examine the movement of distant galaxies, we observe that space itself is stretching, pushing them further away from us. Yet the nature of what this expansion is occurring into remains unanswered. In standard cosmology, space does not require an external environment. It can expand similarly to the pattern on a balloon, growing without needing to account for the air surrounding it, even if we focus solely on its two-dimensional surface. It's hard not to wonder if the fabric of the cosmos is woven into something larger. If such a realm exists beyond our understanding, it may not adhere to the same rules of space or time that we know. It might not even consist of matter, energy, or geometry as we perceive them. Our instruments are crafted to explore what lies within our universe, not what lies beyond. This limitation leaves any broader reality concealed, forcing us to speculate through mathematics and the behavior of distant galaxies. The true nature of cosmic expansion stands as one of the most perplexing questions in modern science. We still grapple with why space appears so smooth on a grand scale. Across billions of light years, the universe reveals a striking uniformity. The temperature of ancient radiation fluctuates only slightly, and matter is distributed in a pattern that is surprisingly even. This smoothness is intriguing because regions that are far apart could never have interacted in the early universe. There simply wasn't enough time for light or any signal to traverse the distances between them. To address this enigma, theories suggest a brief phase of rapid expansion, allowing regions that are now distant to have originated from a small, interconnected area. This concept invites you to reflect on the vastness of our universe and the mysteries that still await discovery. You find yourself contemplating an intriguing idea. While it aligns well with the data at hand, there remain unanswered questions. What sparked that remarkable growth? How did it come to an end? And could alternative explanations hold merit? The uniformity you observe might conceal vital information about processes that unfolded long before the earliest moments we can explore. Space itself may harbor silent clues about a deeper mechanism that shaped the cosmos, even before galaxies took form. The universe could carry subtle imprints from events that transpired before its very birth. The oldest light we can detect is a faint glow that has traversed the vastness of space for nearly the entire history of the cosmos. Although this light has been studied with meticulous care, it might still harbor traces of processes that occurred even earlier than the hot, dense state, often described as the beginning. Certain models of cosmic evolution suggest that ripples, patterns, or slight distortions may have survived from an earlier phase, carried forth as the universe expanded and cooled. These features, if they exist, would be incredibly delicate, hidden within the noise of cosmic data, making them challenging to distinguish from ordinary fluctuations. If you were to uncover them, they could unveil insights about conditions that no current experiment can replicate. Perhaps they might even hint at a prior contraction or a more intricate transition that preceded the familiar expansion we know today. As you ponder these possibilities, Consider the vastness of what remains to be discovered. You are invited to continue this exploration, or perhaps take a moment to rest and reflect on the wonders of the universe. The idea that our universe carries the marks of a bygone era opens up a fascinating perspective. It suggests that the cosmos has a deeper and more intricate narrative than what we can currently perceive. You might ponder the hidden patterns woven into the cosmic web, waiting for discovery. As astronomers chart the distribution of galaxies, they unveil a vast network filled with clusters, filaments, and expansive voids. This complex web bears resemblance to living tissue or neural pathways, illustrating how gravity has sculpted matter on a grand scale. However, what if you're only glimpsing the surface? Beneath that visible layer, there could be profound mathematical connections linking the positions and movements of galaxies in ways yet to be uncovered. Perhaps subtle symmetries exist in the alignment of these structures, or long-range correlations lie hidden, requiring innovative tools to reveal them. Consider how galaxies rotate or cluster. They might adhere to concealed rules that have eluded our understanding until now. As surveys become increasingly detailed, they may expose unexpected order within what appears to be randomness. These emerging patterns could point toward undiscovered physics or hint at early cosmic processes that have left lasting imprints throughout the vast expanse of matter in the universe. Take a moment to reflect on this rich tapestry of possibilities. Would you like to explore further, or perhaps take a moment to rest? The universe may meet its end in ways that are beyond our current understanding. Cosmology presents various potential futures, yet none are guaranteed. If dark energy remains constant, space will continue to expand at an accelerating pace, leading to a gradual isolation of galaxies until the night sky becomes empty and cold. Should dark energy intensify, the expansion could speed up so dramatically that even atoms might be torn apart. Conversely, if dark energy weakens or reverses, the universe might slow down, stop, and eventually collapse into a dense state, possibly giving rise to a new expansion. Other possibilities involve shifts in the fundamental vacuum of space, or alterations in physical laws and processes that we have yet to comprehend. Since we cannot accurately predict the future behavior of dark energy or the stability of the vacuum, we are confronted with a profound uncertainty regarding the universe's ultimate narrative. Each scenario influences matter and time in deeply distinct ways. The expansive future is an open canvas of possibilities, suggesting that our cosmic age is merely one chapter in a much larger story. Some theoretical frameworks even propose that the universe did not originate from a single event, but instead cycles through phases of contraction and expansion, hinting at a continuous process of cosmic creation beyond our current horizon. Imagine for a moment that our cosmic history is just one chapter in an ongoing saga, a narrative woven into a larger tapestry of existence. Each cycle of the universe might leave behind subtle imprints, hints that influence the structure we see around us today. While these concepts are challenging to test, they offer intriguing explanations for the mysteries of uniformity and the patterns we observe. If the universe has indeed experienced multiple cycles, each era could inherit conditions shaped by its predecessors. Picture entire sequences of galaxies, stars, and cosmic evolution rising and fading long before our current time, leaving behind only faint traces, perhaps glimpsed in the earliest moments of our universe's expansion. These cycles could extend far into the future, creating a grand rhythm of creation and transformation that exists just beyond our reach. The question remains, do these patterns truly exist? This uncertainty invites us to consider an alternative to the notion of a singular beginning. We are still searching for answers regarding what triggered the rapid expansion of the early universe. Observations suggest that shortly after its inception, the universe underwent a brief but intense period of growth, smoothing out irregularities and laying the groundwork for galaxies to form. Yet, the cause of this swift expansion continues to elude us, shrouded in mystery. As you reflect on these ideas, allow yourself to contemplate the vastness of possibility that lies within our universe. Proposed explanations for the universe's expansion range from new fields of energy to transitions between physical states and even deeper mechanisms that might involve the very fabric of space itself. Each of these theories strives to explain the characteristics we observe today in ancient radiation and the arrangement of matter. However, none of these ideas have been confirmed, and many predict effects that are incredibly subtle. Without a direct means to explore the conditions of that early universe, you find yourself relying on indirect clues and a careful analysis of cosmic patterns. The true cause of this expansion remains an open question. Understanding it may require insights that unify concepts of gravity, quantum physics, and the very origin of space itself. Imagine that the universe could possess dimensions so small that they elude detection. Some theories propose that beyond the familiar three dimensions of space, there might be extra directions folded into minuscule shapes. These compact dimensions would be far smaller than any current experiment can examine, hidden within the structure of every point in space. Their geometry could influence how particles behave, alter gravitational interactions, or even enable new types of motion that cannot occur in our ordinary understanding of space. As you ponder these ideas, consider the vast possibilities that lie within the unseen dimensions of the universe. Would you like to explore further, or take a moment to reflect on these concepts? Imagine a universe where dimensions are not immediately apparent, yet their influence subtly alters the measurements of particle collisions or leaves faint traces from the early cosmos. To uncover these effects, scientists rely on precise instruments and innovative experimental designs. If these curled dimensions exist, it suggests that our everyday reality is just a glimpse of a much more intricate spatial landscape. Consider the possibility that the universe is constructed on a multi-dimensional foundation, largely hidden from our view. We still ponder whether space itself emerges from something deeper. Recent research proposes that space may not be a fundamental entity. Instead, it might arise from more basic components. In certain models, geometry could emerge from patterns of quantum information or networks of relationships between tiny elements, diverging from traditional notions of location. What if distances, directions, and even the passage of time are merely large-scale manifestations of these underlying structures? Evidence supporting such concepts arises from studies of black holes and quantum physics, where conventional ideas falter and new principles connect geometry with information. While these notions remain speculative, they present a fascinating pathway toward unifying gravity with the realm of particles. As you reflect on these ideas, allow yourself to ponder the mysteries of the universe. Would you like to explore further, or take a moment to rest in this wonder? Imagine for a moment that space is not just what you see, but something that emerges from countless unseen interactions. This perspective invites you to rethink the very fabric of the universe and the nature of your existence. What if the universe is a projection of a more fundamental reality? Certain theories in quantum gravity propose that the three-dimensional world you experience may actually be encoded on a lower dimensional structure, much like a hologram. In these concepts, The vast complexity of space and matter arises from information stored on a surface that has fewer dimensions than the space it describes. This intriguing idea originated from black hole research, where the information needed to define these enigmatic entities appears to correlate with their surface area rather than their volume. If you extend this notion to the entire cosmos, it suggests that reality might possess an unexpected architectural design. While this does not imply that the universe is merely an illusion, it does indicate that your conventional understanding of location and depth may be secondary to deeper principles. As experiments and observations begin to explore these theories, the questions still linger. The idea that the cosmos might be a projection challenges many of your intuitive beliefs and opens up new avenues for understanding the very foundations of physics. In this exploration, you are invited to ponder the mysteries that lie beneath the surface of reality. Dark energy is a force that may be evolving in ways we have yet to comprehend. Astronomers have found that the universe's expansion is accelerating, a phenomenon commonly linked to this enigmatic force known as dark energy. However, the question remains, is this mysterious energy constant, or does it fluctuate over cosmic time? Our current measurements only capture a brief segment of the universe's expansive history, making it extremely challenging to detect any gradual changes. If dark energy does indeed change, it could significantly impact the cosmos's ultimate destiny. It might intensify, causing galaxies to drift apart at an even faster pace, or it could weaken, allowing gravity to slow this expansion in the far-off future. There's even the possibility that dark energy could shift, behaving differently in earlier epochs compared to today. The challenge we face is that dark energy does not interact directly with matter or light. We can only infer its existence by observing the movement of galaxies and the structure of space itself. Any subtle variations might be concealed within the uncertainties of our current understanding, patiently waiting for more precise measurements or innovative methods to chart cosmic history. The essence of dark energy stands as one of physics' most profound enigmas. Similarly, dark matter might be something entirely beyond our grasp. We can see its effects as it surrounds galaxies and influences the large-scale structure of the universe, yet its true nature remains elusive. As we continue to explore these mysteries, we invite you to ponder the vastness of what lies beyond our current knowledge. You find yourself contemplating a mysterious substance that eludes our senses. This invisible matter neither emits light nor interacts significantly with the atoms we know. Although various theories propose new particles to explain it, another intriguing possibility arises. What if dark matter doesn't belong to the familiar forces and interactions at all? Imagine it as part of a realm of physics that barely touches our reality. In this scenario, dark matter could possess its own unique particles, movements, and internal processes, operating in a shadowy framework that rarely affects ordinary matter except through the force of gravity. This perspective opens up vast worlds of behavior that remain hidden from every detector we have on Earth. If dark matter indeed exists outside the boundaries of known physics, unraveling its nature will demand ideas that stretch beyond conventional approaches. Its very presence might suggest that our understanding of reality captures only a small fraction of what truly exists. Consider the possibility that particles are passing through you right now, undetected by our instruments. Even within the known laws of physics, countless particles constantly traverse space. Some, like neutrinos, are familiar to us, moving through matter with minimal interaction. Yet others may lie just beyond our current comprehension, drifting through planets, stars, and even ourselves without leaving any trace. As you reflect on this, you may wonder what other secrets the universe holds, hidden in the shadows of our understanding. The journey to uncover these mysteries invites you to continue exploring, or perhaps to pause and ponder the vastness of it all. Imagine a world where interactions are so faint or peculiar that they evade our current instruments entirely. Some theorists suggest the existence of particles that seldom collide with ordinary atoms, while others propose entities that defy conventional categories of matter and energy. Picture the Earth immersed in a vast sea of undetected particles, quietly influencing cosmic evolution, yet remaining hidden from our sight. As each new generation of detectors ventures deeper into this enigmatic landscape, they seek signs of these elusive particles in soft glimmers of light, gentle vibrations, or rare collisions. The thought that unknown particles might be flowing through us at every moment hints at a reality that lies just beyond our grasp. Dark matter could be weaving structures as intricate as those we can see in the universe. Although it remains invisible, its gravitational pull shapes everything around it. Cosmic evolution models frequently illustrate dark matter coalescing into halos, guiding the formation of galaxies. However, these halos might not be mere clouds. They could consist of layers, clumps, waves, or patterns crafted by interactions within the dark sector. If dark matter possesses its own forces or families of particles, it may be capable of forming structures as diverse as those composed of atoms. Take a moment to reflect on this vast hidden reality. What mysteries might be waiting just beyond your perception? Imagine a universe where unseen structures influence the very fabric of space. These structures do not emit light, yet they hold the power to shape the motions of stars and gas, guiding the formation of galaxies in ways we have yet to fully understand. Some simulations propose that dark matter could weave intricate filaments within cosmic halos or support enduring patterns that dictate how galaxies rotate. To uncover these hidden architectures, we need highly detailed observations and innovative theoretical frameworks. This notion that an invisible realm coexists alongside the visible universe invites us to reflect on the limitations of our current perspective. Dark energy, often perceived as a force that merely drives the expansion of space, may actually interact with matter in ways we have yet to observe. While most interpretations treat it as a separate entity, some theoretical models suggest a faint connection between dark energy and the particles that compose stars and galaxies. If such an interaction is real, it might lead to subtle shifts in particle masses or the strength of forces over immense timescales. These minute changes could accumulate throughout cosmic history, leaving traces in the arrangement of galaxies or influencing the rate at which structures emerge. So far, we have not found clear evidence of these interactions, yet the door remains open to possibility, as the effects we seek could be incredibly small, hidden in the vastness of the cosmos. As you ponder this intricate dance of forces, consider how much more there is to discover in the universe around you. Imagine a future where surveys of distant galaxies unveil the hidden dialogue between dark energy and matter. If this connection is real, it could transform your understanding of the universe's evolution, revealing a bridge between two of its most enigmatic components. Consider the possibility that dark matter isn't just a single entity, but may consist of various types, hidden in plain sight. While most discussions assume dark matter is made up of one kind of particle, nature often embraces diversity. Just as ordinary matter includes atoms, molecules, plasma, and dust, dark matter could be equally varied. Some forms might be cold and slow-moving, while others could be warm and fast. There may even be types that bind into composite structures through interactions within the dark sector. Each of these dark matter types would influence galaxy formation in unique ways, creating a more intricate landscape than simple models suggest. Since dark matter doesn't emit light, this diversity remains invisible to us. Instead, it might reveal itself through subtle changes in the motion of stars or the shapes of galaxies. To grasp this complexity, you would need new methods for analyzing cosmic data and innovative theories that allow dark matter to possess an internal structure. As you ponder these possibilities, consider the vastness of what lies beyond, waiting to be understood. You are invited to continue this journey of exploration, or take a moment to reflect on the mysteries of the universe. The concept of multiple unseen elements suggests that the universe's darker aspects could be far more complex than we realize. Dark energy might point to a deeper layer of reality that eludes our perception. The discovery of accelerated expansion has compelled physicists to consider that the vacuum of space harbors energy with peculiar properties. This energy behaves differently from matter or radiation, implying that space itself possesses an underlying structure that affects how it expands. Some theories connect dark energy to quantum fields that permeate all of space, while others associate it with geometric characteristics arising from fundamental principles. If dark energy indeed reflects a hidden dimension of reality, then our common understanding of space may only scratch the surface. The behavior of dark energy could unlock insights into this deeper framework, yet we currently lack the means to explore it directly. Observations of distant supernovae, galaxy clustering, and the cosmic background provide valuable hints, but the complete picture remains elusive. Dark energy might be the clearest indication that reality holds layers yet to be discovered. Furthermore, dark matter could represent a shadow of processes occurring in higher dimensions. Some theoretical models suggest that our universe may contain more spatial dimensions than we can perceive. If higher dimensions exist, dark matter might simply be a reflection of processes happening within them. In this perspective, the particles we detect solely through their gravitational effects could be entities moving or interacting in directions that our ordinary senses cannot access. Their seeming invisibility may naturally arise from their higher dimensional nature. These particles would interact weakly with familiar matter because they exist in different layers of reality, yet their mass would still exert a gravitational pull on stars and galaxies. This concept provides potential explanations for the peculiar behavior of dark matter compared to ordinary particles, and why it forms vast halos around galaxies. To detect these effects, we would need to observe small deviations in gravitational behavior or search for evidence of motion in these extra-dimensional realms. If dark matter is indeed tied to higher dimensions, uncovering its true nature could revolutionize our understanding of space itself. Imagine entire stars composed primarily of dark matter. If dark matter can clump together under the influence of gravity, it might accumulate in sufficient concentrations to form compact objects. In certain cosmological scenarios, dark matter could collapse into dense regions that behave like stars, yet without undergoing nuclear reactions or emitting visible light. As you ponder these possibilities, consider how this knowledge could reshape our view of the universe. Would you like to delve deeper into these intriguing concepts, or take a moment to reflect? Imagine a universe filled with dark stars, hidden from our view. These celestial bodies remain nearly invisible to telescopes that depend on electromagnetic radiation. Instead, their existence might be detected solely through their gravitational effects. Some theories suggest that dark matter particles could release energy in unique ways, allowing these stars to emit faint light that we have yet to discover. Others envision them as cold, silent entities drifting through galaxies, leaving behind only subtle gravitational traces. To uncover such elusive objects, scientists would need to meticulously map stellar movements or observe gravitational lensing. The discovery of dark stars would introduce a whole new category to our cosmic understanding, revealing that the universe harbors types of stellar bodies unlike anything we have encountered before. Dark matter may also hold secrets about ancient epochs of the cosmos. Because it interacts so minimally with ordinary matter, dark matter has preserved its original properties throughout nearly the entire history of the universe. While atoms have been torn apart, fused, and reshaped within stars, dark matter has largely remained unchanged. Its current distribution still mirrors the conditions that existed long before galaxies took shape. If we can decipher its structure, we might unlock insights into epochs that no light can illuminate. Take a moment to reflect on the mysteries that still lie within the cosmos. You are part of this journey of discovery, and as we explore further, the universe may reveal its hidden wonders. Slight variations in dark matter density may reveal events from the early universe or transitions that happened before the emergence of familiar particles. To map these patterns, we need to observe how galaxies move within their halos and how matter clusters across different scales. Each measurement offers a glimpse into the ancient landscape that shaped the cosmos. Dark matter acts as a quiet record keeper, preserving information in its arrangement throughout space. Black holes present a fascinating mystery. They may contain regions where the very fabric of reality begins to break down when matter collapses under its own gravity to form a black hole. General relativity predicts that space-time curves increasingly toward the center. Eventually, the equations indicate that this curvature could become infinite. This doesn't suggest a literal infinity, but highlights the limitations of our current theories. Under such extreme conditions, the familiar rules of space, time, and physics may dissolve, making quantum effects significant. Yet, we still lack a complete theory that unifies quantum mechanics with gravity. Consequently, the interior of a black hole remains an unsolved frontier, inviting us to reflect on the mysteries that lie ahead. Would you like to explore this topic further, or take a moment to rest? You find yourself pondering the mysteries of the universe, where physical concepts that seem clear and smooth in our everyday lives become perplexing. In this enigma, the very idea of location might lose its meaning. This captivating realm is shrouded from our view by the event horizon, a boundary beyond which no signal can transmit information back to us. What lies within remains one of the most striking reminders of our incomplete grasp of reality. Imagine the center of a black hole. While classical theory suggests it is a singularity, a point of infinite density, many researchers propose that nature cleverly sidesteps true infinities. Alternative theories suggest that quantum effects could transform this singularity into something far more intricate. Some envision a region of incredibly high, yet finite density. Others describe a minuscule sphere where quantum pressure effectively balances gravity. There are even ideas of a surface where space-time experiences a phase transition. These intriguing possibilities hinge on understanding how quantum gravity functions. However, as this field is still evolving, a definitive answer continues to elude us. Observing black holes directly doesn't unveil their centers, leaving us to rely on indirect evidence. The behavior of gravitational waves, the motion of matter near the event horizon, and the long-term stability of black holes might provide the clues we seek. As you reflect on these concepts, feel free to continue exploring or take a moment to rest in the wonder of this cosmic mystery. Every scenario presents a unique internal structure, hinting that black holes could harbor exotic states of matter or geometries beyond our laboratory studies. Imagine the possibility of pathways through black holes leading to entirely different realms. The mathematics of general relativity introduces solutions suggesting that black holes might connect distant locations or even other universes through hypothetical bridges. These structures, while fascinating, are often unstable, collapsing too quickly for anything to traverse. Yet they remain captivating possibilities. What if quantum effects could enhance the stability of these pathways? In specific models, a traveler attempting to cross these thresholds would encounter immense tidal forces and unpredictable physical conditions, making such a journey purely theoretical for the moment. Some theories even suggest that what appears as a black hole from the outside could be linked to a different region, one resembling a white hole from within, ejecting matter instead of absorbing it. These concepts emerge naturally from the equations of gravity. However, we still lack concrete evidence to confirm whether any of these ideas correspond to actual physical entities. Yet the notion that black holes might act as gateways hints at a universe that is far more interconnected than our senses would lead us to believe. As you ponder these possibilities, consider the mysteries that lie beyond our current understanding. Would you like to explore this further, or perhaps take a moment to reflect? Black holes hold secrets about information that challenge our understanding. You might wonder what happens to the information contained in matter that falls into a black hole. Quantum theory tells us that information cannot simply vanish, yet classical black holes seem to wipe away the details of anything that enters them. This contradiction has sparked intriguing ideas, suggesting that information could be encoded in subtle patterns at the event horizon or stored in the quantum states of the gravitational field. Some theories propose that the event horizon functions like a physical surface, teeming with countless microscopic degrees of freedom. Others suggest that information might slowly seep out through radiation over the black hole's lifetime. However, none of these concepts are definitively proven, and each one brings forth new questions about how information exists within the fabric of space-time. Unraveling this mystery could unveil a profound link between quantum theory and gravity, illuminating how the universe retains its history, even in the most extreme conditions. You might find it fascinating to consider the possibility of tiny primordial black holes scattered throughout the cosmos. In the early universe, certain density fluctuations could have been significant enough for some regions to collapse directly into these small black holes. This exploration invites you to reflect on the nature of existence and the hidden intricacies of our universe. Would you like to delve deeper into these cosmic wonders, or perhaps take a moment to ponder their implications? These ancient objects likely didn't originate from stars, which means their sizes could vary significantly, from very small to quite large. If they do exist, they might play a role in dark matter or subtly influence the evolution of the cosmos. Some may have completely evaporated, while others could still be drifting unnoticed through galaxies. Their presence might be hinted at through gravitational lensing of distant stars, changes in the motion of celestial bodies, or faint radiation emitted during their final moments of evaporation. Despite extensive searches, no definitive detection has been made yet. The possibility of primordial black holes remains intriguing, as they could bridge the gap between our understanding of the early universe and the mystery of dark matter. If they are indeed real, they would offer a unique glimpse into the conditions that existed long before the first stars lit up the sky. You may wonder what lies at the very edge of a black hole. This boundary, known as the event horizon, separates the black hole's interior from the outside universe. It isn't a solid surface, rather it's a region where escape becomes impossible. While general relativity provides insights into how the horizon functions, quantum effects add layers of complexity to our understanding. The horizon of a black hole is a fascinating concept, emitting radiation through complex quantum processes, though the exact mechanism remains elusive. Some theories propose that this horizon has a multifaceted structure shaped by quantum information, while others envision it as a smooth boundary without distinctive features. Since we cannot observe the horizon directly, our comprehension is largely based on theoretical frameworks. You might find it intriguing that the behavior of particles, light, and information near this boundary could provide vital insights into the unification of physics. The edge of a black hole represents a frontier where our current understanding of physical laws encounters its limits. This makes it an essential area of exploration for those seeking a deeper grasp of gravity and quantum mechanics. Imagine that black holes could evaporate in ways that remain unseen. Quantum theory suggests they emit radiation, gradually losing mass over extraordinarily long time frames. While this idea holds strong theoretical support, it has yet to be directly observed, as even the smallest black holes evaporate far too slowly for our current detection methods. Some models propose that this evaporation might involve bursts of energy or shifts in the spectrum of the emitted radiation during the later stages. Others speculate that the final moments of a black hole's life could unveil new physics, potentially involving exotic particles or transitions in the very fabric of space-time. As you ponder these mysteries, consider how much there is still to learn. Feel free to continue exploring this captivating topic, or take a moment to reflect on the wonders of the universe. Imagine a scenario where evaporation behaves differently than we expect. This change could reshape our understanding of energy conservation, information preservation, and even the life cycle of black holes. To detect these intriguing signals, we might need an unexpectedly small black hole situated near Earth, or perhaps a new technique to observe the faintest radiation scattered across the universe. The ultimate fate of black holes remains a mystery, one that carries significant implications for the very fabric of the cosmos. It's fascinating to consider that some black holes may have formed even before the first stars lit up the night sky. Typically, black holes emerge from the collapse of massive stars nearing the end of their life cycle. Yet, the conditions in the early universe could have allowed black holes to arise directly from dense regions of primordial gas. These primordial black holes would predate the formation of stars and galaxies, serving as seeds that shaped the early structure of the universe. Their growth could provide answers to the enigma of how some supermassive black holes reached staggering sizes so rapidly, a puzzle that continues to captivate astronomers. Moreover, these early black holes may have interacted with the surrounding gas, potentially influencing the rate at which the first stars formed. Observations of ancient quasars reveal the existence of extremely massive black holes during a time when the universe was still in its infancy. This glimpse into the past invites us to ponder the intricate dance of cosmic evolution. Would you like to explore this captivating journey further, or perhaps take a moment to reflect on these wonders? To understand the emergence of these cosmic giants, you might consider the existence of an earlier generation of black holes. These ancient entities could have formed through processes distinct from stellar evolution, offering a glimpse into the universe's earliest moments. Black holes may influence the cosmos more profoundly than you realize. Often depicted as solitary figures, their reach extends far beyond their immediate vicinity. The largest galaxies tend to harbor massive black holes at their cores. The energy released when matter spirals into these giants plays a crucial role in shaping the entire galaxy's growth. Jets of high-energy particles can heat or disperse surrounding gas, effectively regulating star formation across vast expanses. Even the smaller black holes have their part to play. They can trigger bursts of radiation or disturb the motion of nearby matter, influencing their environments in significant ways. On a cosmic scale, the combined activities of black holes may determine how structures evolve, how galaxies cluster, and how gas circulates between different regions. Though these effects are often indirect, they can reshape vast areas of space over immense stretches of time. As we continue to uncover the role of black holes in cosmic evolution, it becomes clear that they are not merely the final chapters of stellar life. Instead, they serve as engines driving large-scale transformations in the universe. Take a moment to reflect on this intricate dance of cosmic forces. Imagine a universe filled with hidden black holes, entities that emit almost no light. Most of the black holes we know about are identified through the radiation generated by hot gas spiraling into them. However, many black holes may exist in tranquil environments where little matter drifts inward. These enigmatic objects remain almost entirely dark, detectable only by their gravitational influence. Some of these black holes might wander through the cosmos alone, while others could be found in the outskirts of galaxies or nestled within star clusters. Discovering them demands careful analysis of stellar movements, gravitational lensing, or rare interactions with nearby objects. It's possible that the universe harbors far more black holes than our current observations reveal, with many still hidden from our view. These silent black holes offer vital insights into stellar evolution, galactic dynamics, and the unseen remnants scattered across the cosmos. Their existence serves as a reminder that much of the universe consists of entities that reveal themselves solely through subtle gravitational effects. As we explore these mysteries, we ponder whether gravity behaves differently on scales larger than galaxies. Astronomers have measured gravity with remarkable precision within our solar system and within galaxies. Yet, when we look at the vastness of the universe, it becomes increasingly challenging to determine if the familiar equations still hold true. Take a moment to reflect on these cosmic wonders and consider what other mysteries await us in the depths of space. You find yourself contemplating the intricate motion of galaxies within clusters and the growth of vast cosmic structures. The ancient light from the universe reveals a delicate balance, all governed by the force of gravity acting over immense distances. Some observations suggest there are subtle mismatches between what we predict and what we actually observe. This raises an intriguing possibility. Gravity may change its behavior ever so slightly when stretched across the vast expanses of space. Imagine these variations, though tiny, having the potential to influence the universe's expansion or the formation of cosmic structures. Some theories propose that gravity might weaken, strengthen, or even shift its form when interacting with the emptiest regions of space. Others contend that these changes could arise because the universe is not uniformly structured. To truly understand these possibilities, we need deeper surveys, more refined models, and innovative ways to test gravity across cosmic landscapes that far exceed the confines of our laboratories. Hidden forces may be acting across these vast distances, shaping the cosmos in ways we have yet to fully grasp. Beyond gravity, the universe might also harbor long-range forces that barely impact everyday matter, but subtly influence the grand tapestry of the cosmos. These hypothetical forces could dictate how galaxies move and how clusters evolve, though they may act with extreme weakness, rendering them difficult to detect within our solar system. Their influence could extend across billions of light years. As you ponder these cosmic mysteries, consider the vastness of what remains to be discovered. The universe invites you to explore further, to question, and perhaps to rest in the wonder of it all. New theories suggest that unseen forces could permeate all of space, shaping the behavior of dark matter and interacting with regular matter through subtle channels. These forces might clarify the unusual movements observed within galaxies and the unexpected patterns seen in cosmic structures. To detect them, we need precise observations of distant celestial objects, careful comparisons with theoretical predictions, and an open mind to the possibility that the universe contains influences beyond our current understanding. If these hidden forces exist, they would offer a richer and more complex view of cosmic behavior. Gravity may be intertwined with quantum information in ways that remain hidden to us. Insights from quantum theory and general relativity are increasingly hinting that space-time could be linked to the flow of information. In certain frameworks, the curvature of space might arise from the arrangement of microscopic quantum states, with gravity emerging as a large-scale effect of how this information is organized. This perspective connects the bending of light, the movement of planets, and the behavior of black holes to deeper patterns involving entanglement and quantum correlations. As you reflect on this, consider the vastness of the universe and the mysteries it holds. And would you like to explore these ideas further, or perhaps take a moment to ponder their implications? Imagine a universe where classical gravity serves as a visible expression of a deeper informational fabric. This intriguing idea draws support from studies of black hole thermodynamics and the mathematical relationships between geometry and quantum systems. However, no direct experiments have yet confirmed this connection. Understanding it may require new tools that bridge the divide between quantum physics and gravity. This possibility suggests that the universe's geometry might not be fundamental. Instead, it could reflect hidden rules shaping reality. The cosmos may harbor gravitational phenomena beyond our current imagination. Most of what we understand about gravity stems from observing planets, stars, black holes, and large-scale structures. Yet the universe is so vast that there could be phenomena occurring under extreme conditions or in unexplored regions. Consider the existence of exotic gravitational configurations where space-time behaves in ways we cannot yet describe. Strange objects might bend space in asymmetrical or unpredictable patterns. In areas with unusual forms of matter, entirely new gravitational effects could emerge, leaving only faint or indirect traces in the data we observe. As you reflect on these possibilities, allow your curiosity to expand. What might be waiting to be discovered? As our instruments advance, you might discover hints of unfamiliar behaviors in the universe. These could emerge in gravitational wave signals or anomalies in the distribution of distant galaxies. The full range of gravitational possibilities likely extends far beyond our current theories, waiting to be unveiled in the vast reaches of the cosmos. Consider the idea that gravity might not be constant. In some theoretical frameworks, it could vary slightly over time or across space. These variations might stem from fields that evolve slowly across cosmic distances, or from interactions between gravity and unknown components of the universe. If gravity fluctuates gently, these changes would be too subtle to detect on Earth. yet they could significantly influence cosmic evolution over vast timescales. Regions where gravity is slightly stronger could form structures more rapidly, while those with weaker gravity might experience delays in galaxy growth. Observations of distant clusters and the cosmic web may reveal faint signs of such variations. However, distinguishing these from ordinary cosmic variability is a challenge. It requires meticulous analysis of extensive data sets and advanced simulations. As you reflect on these possibilities, consider the mysteries still waiting to be unraveled. The cosmos is vast, and each discovery brings you closer to understanding its intricate tapestry. Feel free to continue exploring or take a moment to rest. The universe is patient, and so are you. Imagine a world where gravity shifts, even slightly. This notion suggests a profound and dynamic foundation behind one of nature's most familiar forces. Picture gravity leaking into dimensions beyond what we can perceive. Some theories propose that gravity isn't limited to the three-dimensional space we know. Instead, it may extend into hidden spatial directions unseen by our senses. If this is true, gravity would seem weaker than we expect in our three-dimensional world, as part of its influence reaches into these concealed dimensions. This perspective could shed light on why gravity feels so much weaker compared to other forces. Moreover, it might create unique patterns in experiments aimed at detecting subtle deviations from Newtonian behavior. On a cosmic scale, gravity seeping into higher dimensions could affect how structures in the universe develop or even contribute to the accelerated expansion we observe. While no definitive evidence has emerged, this possibility captivates the imagination. It aligns seamlessly with theories striving to unify the fundamental forces of nature. Envisioning extra-dimensional effects could transform our comprehension of space, matter, and the intricate dance of the cosmos. As you ponder these ideas, consider the vast potential they hold for reshaping our understanding of reality. The gravitational constant may not be uniform everywhere. This constant, which determines the strength of gravity, is crucial for every astronomical calculation. However, we remain uncertain whether it remains fixed across the vastness of space and time. If it varies even slightly, it could significantly impact the formation of stars, the behavior of galaxies, and the overall evolution of the universe. Subtle shifts might arise from interactions with unknown fields or from processes that originated in the early universe. Observations of distant celestial objects provide indirect tests of this theory. Yet, distinguishing genuine variations from typical astrophysical differences proves to be quite challenging. Some studies have sought evidence by examining the timing of pulsars, the brightness of supernovae, or the distribution of galaxy clusters. To date, the results remain inconclusive. If future measurements reveal changes in the gravitational constant, it would suggest that gravity is not merely a simple, universal force. Instead, it might be a dynamic quantity shaped by deeper layers of physics. The nature of gravity during the universe's infancy remains a mystery. As we journey back through cosmic history, conditions become increasingly extreme, with rising temperatures and densities, and quantum effects start to play a significant role. Consider the implications of this knowledge. What mysteries of the universe might unfold as we continue to explore? In today's exploration, we find ourselves grappling with the limitations of general relativity when it comes to describing gravity. You realize that to truly understand this fundamental force, we must seek a theory that unifies gravity with the principles of quantum physics. However, this quest remains unfinished, leaving us with unanswered questions about the curvature of space and the behavior of matter during the universe's earliest moments. You may wonder where the answers lie. Clues could be hidden in the ancient cosmic light or in the distribution of large-scale structures throughout the universe. The behavior of gravitational waves may also hold key insights. These hints suggest that gravity might have acted differently in the early universe, potentially allowing for phenomena that we no longer observe today. Imagine the early universe as a unique laboratory, with conditions that we cannot replicate here on Earth. Understanding gravity in that primordial environment stands as one of the most pressing challenges in cosmology today. You might consider that there could be particles responsible for mediating gravity in subtle ways. In quantum field theory, forces are typically transmitted by particles. But if gravity operates similarly, it might involve a hypothetical particle that interacts extremely weakly, making it nearly impossible to detect in experiments. The existence of such a particle could influence gravitational waves, alter the behavior of black holes, or subtly change how matter clusters on large scales. As you reflect on these ideas, you are invited to continue this journey of discovery, or take a moment to rest and ponder the mysteries of the universe. Some theories suggest that there are families of particles, each playing a distinct role in the overall behavior of gravity. To detect these particles, we would need methods capable of isolating incredibly faint signals or observing effects that build up over vast cosmic distances. These particles might also interact with unknown fields or dimensions, adding complexity to their behavior. If they truly exist, they could offer a pathway to unify gravity with quantum theory, unveiling the microscopic structure behind the force that shapes our universe. Imagine gravity as something deeper than just space-time. The familiar view of gravity as the curvature of space-time might merely be an approximation of a more fundamental process. In certain models, gravity arises from the collective behavior of microscopic constituents that do not resemble space at all. These constituents could be quantum bits of information, relational structures, or other entities governed by rules that differ from any classical theory. In this perspective, space-time itself becomes a large-scale phenomenon, much like temperature emerges from the motion of microscopic particles. If gravity is indeed emergent, then grasping its true nature requires us to identify the underlying components and the principles that guide them. This exploration invites you to reflect on the deeper connections within the universe. Connections between thermodynamics, information theory, and black hole physics provide intriguing evidence for a fascinating idea. This concept, though still speculative, offers a unified approach to link gravity with quantum mechanics. It proposes that our understanding of space, time, and curvature might be secondary effects shaped by an unseen foundation, influencing how the universe operates at its most fundamental level. Consider the first stars, entities unlike anything we see in the modern universe. Astronomers believe these early stars formed from pristine gas, composed solely of hydrogen and helium, the simplest elements birthed in the first moments of cosmic history. Lacking heavier elements to cool the gas effectively, these stars likely grew far more massive than those we observe today. Some theories suggest they reached masses hundreds of times greater than our sun, burning at extraordinary temperatures and living only for brief moments before collapsing or exploding. The interiors of these colossal stars may have generated the first heavy elements, seeding later generations of stars and profoundly shaping the universe's chemistry. Because these magnificent giants lived fast and died young, they disappeared long before any galaxy reached maturity. Isn't it remarkable to think about how these ancient stars contributed to the fabric of our universe? To uncover traces of the first stars, you must delve into faint signals left by ancient cosmic light or gaze at distant galaxies where their influence can still be felt in the gas distribution. The essence of these early stars remains a mystery, yet they lay the groundwork for everything that came after. You might wonder how the first galaxies formed so swiftly. When telescopes peer back into the cosmos's infancy, they reveal galaxies that seem surprisingly advanced, despite the brief time since the first stars ignited. These early galaxies showcase structured regions, vigorous star formation, and even central black holes. Standard models suggest that creating such complex systems should take longer than the universe has allowed. This discrepancy has sparked renewed interest in understanding how gas collapses, fragments, and ignites under primordial conditions. You may find yourself questioning whether our theories accurately depict how matter behaved during those initial few 100 million years. New observations consistently uncover bright and organized early galaxies, adding depth to the puzzle. These findings suggest that the conditions in the early universe might have encouraged rapid growth through mechanisms that remain elusive in current simulations. As you reflect on this cosmic journey, consider the mysteries that still await discovery. Would you like to continue exploring, or perhaps take a moment to rest? Understanding the origins of the universe involves delving into the mysteries of the first galaxies. These ancient galaxies hold crucial insights into how the large-scale structure of the cosmos developed from its initial fluctuations. Some of them appear far older than they logically should, presenting a puzzling dilemma. When we observe extremely distant galaxies, we often find systems that seem too massive, too bright, or too chemically enriched for their age. These galaxies formed during the universe's infancy, yet they exhibit characteristics typical of much later periods. The stars within them can show signs of earlier generations, despite the fact that there shouldn't have been enough time for multiple cycles of star formation and evolution. This contradiction poses a challenge to our current models of galaxy growth. Scientists are prompted to explore whether star formation was more efficient in the early universe, or if there are unknown mechanisms that accelerated the development of these galaxies. Some may have experienced rapid mergers, while others could have collapsed quickly from dense pockets of primordial gas. Each of these explanations carries significant implications for our understanding of cosmology, suggesting that we might need to refine our picture of early cosmic timelines. These ancient outliers serve as compelling markers of the unexplained processes that shaped the universe's earliest structures. As you reflect on this, consider how much more there is to discover about our cosmic origins. Imagine stars that are almost entirely composed of exotic particles. While most stars shine through the familiar process of nuclear fusion involving common elements, some intriguing theories suggest the existence of stars made up of entirely different matter. These hypothetical stars could harness dark matter interactions as their energy source, or they might contain particles that defy the usual rules of nuclear physics. If such stars exist, their behavior would be quite different from that of ordinary stars. Their temperatures, lifespans, and internal structures could vary dramatically from what we typically expect. They might emit unusual light spectra or produce neutrino signatures that are unlike any known stellar processes. Detecting these exotic stars would require meticulous searches for objects that seem too dim, too bright, or too stable for their mass and age. These extraordinary stars would provide us with direct insights into unfamiliar physics, revealing that starlight may not always originate from the same processes that govern our familiar cosmos. Now consider the mystery of supermassive black holes. These colossal black holes Millions or even billions of times the mass of our Sun can be found in galaxies across the universe. Yet observations reveal that some of these giants were already massive when the universe was still in its infancy. What could explain such rapid growth? This remains one of the intriguing questions that continues to challenge our understanding of the universe. The rapid growth of massive objects presents a fascinating challenge. Current processes of accretion and merging don't seem efficient enough to account for their swift formation. Various theories attempt to solve this mystery. Some suggest that the first black holes originated from stars significantly larger than any we observe today. Others propose that entire clouds of gas collapse directly into black holes without forming stars first. Another intriguing possibility is that early cosmic environments allowed for unusually high feeding rates, and each of these explanations requires conditions that differ from those we see in the modern universe. Understanding how these giants emerged so early is crucial. Their existence influenced the evolution of the first galaxies and shaped the broader development of the cosmos. Interestingly, some galaxies appear to lack dark matter, raising questions we cannot yet answer. Dark matter is generally believed to be vital for galaxy formation, providing the gravitational framework that keeps stars and gas bound together. However, a handful of observed galaxies contain far less dark matter than we expect, and in some instances, almost none at all. The stars in these galaxies move more slowly than predicted, suggesting that dark matter does not dominate their mass. These peculiar systems challenge our widely accepted notions about how galaxies form and evolve. Isn't it intriguing to think about the mysteries still waiting to be uncovered in the universe? You might find yourself contemplating the vastness of space and the secrets it holds. Feel free to explore these thoughts further or take a moment to reflect. Some theories suggest that interactions with neighboring galaxies might have stripped away dark matter, while others propose these galaxies could have formed through processes we have yet to comprehend. By observing them more closely, you may discover whether they truly challenge our understanding, or if hidden complexities in their structures conceal the presence of dark matter. These galaxies, though rare, are significant, offering unexpected insights into the diversity of cosmic evolution. Imagine entire galaxies composed mostly of invisible matter. While some galaxies seem to lack dark matter, others might consist almost entirely of it. Such galaxies would have very few stars, making them extremely faint and difficult to detect. Their existence could only be inferred through their gravitational effects on nearby objects or by the subtle bending of background light. If these dark-dominated galaxies exist, they might explain part of the universe's missing matter and provide valuable clues about how dark matter behaves on a galactic scale. They could form in regions where normal matter struggles to cool efficiently, or where star formation is limited. Studying these galaxies could enhance your understanding of how structures form in the dark sector and how galaxies assemble under various initial conditions. As you reflect on these possibilities, consider the vastness of the universe and the mysteries it still holds. You are invited to continue exploring these cosmic wonders, or take a moment to rest and ponder. Imagine a world where the discovery of just a few unusual objects reshapes our understanding of galaxies. These objects may not fit into any existing category. Astronomers typically group stars based on characteristics like temperature, mass, and composition. However, surveys sometimes uncover celestial bodies that defy these straightforward classifications. Some of these anomalies seem too cool to be stars, yet too warm to be planets. Others display chemical signatures or brightness patterns that don't align with established models. These peculiarities might signify previously unknown stages of stellar evolution, or entirely new types of objects shaped by unique physical processes. They could be remnants of unusual formation histories, or products of environments that exist nowhere else in the universe. To truly understand these mysteries, we need to engage in detailed observation and think creatively about how matter behaves under unexpected conditions. Each anomaly pushes the limits of our established classifications, reminding us that the universe may harbor forms of stellar structure that are rare, fragile, or simply unfamiliar. There could be ancient cosmic structures waiting to be discovered. While the observable universe is filled with clusters, filaments, and other vast formations, our surveys represent only a small slice of the cosmos. What else might be out there, hidden from our view? As we continue to explore, the possibilities are endless. Imagine a universe filled with mysteries, stretching beyond the limits of our current instruments. You might find structures that are older, larger, or more intricate than anything we've ever mapped. These could be vast collections of galaxies, uniquely shaped cosmic voids, or patterns left by ancient processes that are no longer at work. Some of these features may be so faint or diffuse that they seamlessly blend into the background. Others might exist just beyond what we can currently observe. As our telescopes and analytical techniques evolve, you could uncover hints of these hidden structures. These hints may come through gravitational effects, subtle distortions of ancient light, or unexpected alignments in the cosmos. Discovering these elements would significantly enhance your understanding of how matter has arranged itself over cosmic time. Consider the lives of stars. Most follow a predictable path from formation to their final collapse. Yet, some stars present a puzzle, their deaths not aligning with standard explanations. You may notice certain explosions that appear either too bright or too faint for their expected mass. Others leave behind unusual remnants or emit energy in ways that challenge our current understanding of physics. Some stars might collapse directly into black holes without any visible signs, while others could experience a partial collapse, resulting in exotic cores. The universe is full of wonders waiting for you to explore. Would you like to continue this journey, or take a moment to reflect? You notice that the peculiarities of stellar endings hint at intricate processes that current models struggle to explain. Observing these events demands swift observations, a wide range of wavelengths, and thoughtful comparisons with theoretical predictions. The varied ways stars meet their end reveal that the journey of stellar evolution is still shrouded in unsolved mysteries. Imagine neutron stars, which may conceal states of matter that remain unknown to us on Earth. Within a neutron star, matter is compressed to densities that far exceed what we can achieve in our laboratories. In such extreme environments, atoms lose their familiar forms. Electrons are compelled to merge with protons, creating a vast sea of neutrons, tightly packed with hardly any empty space in between. Yet, even this explanation might be overly simplistic. The core's pressure could escalate to such levels that neutrons disintegrate into their fundamental particles or transform into entirely new states of matter. Some theories suggest the existence of a fluid made of quarks, while others envision strange particles emerging only under extreme compression. These extraordinary conditions may reveal behaviors that are uniquely found nowhere else in the universe. Since we cannot directly investigate the interiors of neutron stars, we gather insights from vibrations, cooling patterns, and the interactions of these stars when they exist in binary systems. This exploration invites you to ponder the mysteries that lie within. Would you like to continue this journey of discovery, or take a moment to reflect. Every observation you make reveals a tantalizing hint, yet the true essence of what lies within remains a captivating and unresolved mystery. Imagine objects denser than neutron stars, but not quite black holes. In our known universe, we encounter white dwarfs, neutron stars, and black holes. However, some theories propose the existence of entities that bridge the gap between the last two. These hypothetical bodies could consist of exotic particles or peculiar arrangements of matter that resist collapse, even under extreme densities. They might be smaller and heavier than typical neutron stars, yet not compressed enough to create an event horizon. If such objects truly exist, they would challenge our understanding of the nuclear forces that bind matter together. Their signatures might be concealed within perplexing mass measurements or in the strange behaviors observed in binary systems. To distinguish them from familiar objects, you would need to conduct precise observations on how they bend light and interact with their companions. These ultra-dense bodies could serve as a natural laboratory for exploring physics beyond what is currently known, unveiling new layers of complexity in how matter behaves under pressures far greater than anything experienced on Earth. It's even possible that some neutron stars might entirely transform into exotic matter. As certain neutron stars accumulate mass, either through accretion or over long periods of evolution, their internal pressure can reach levels where neutrons become unstable. In some theoretical models, this instability leads to a transformation into strange matter or quark matter, resulting in an object that is fundamentally different from its original state. This change might happen suddenly or unfold gradually, affecting the star's rotation, magnetic field, and thermal characteristics. If the entire interior undergoes this conversion, the star evolves into a new type of compact object with distinct density and structure. Detecting such transitions would necessitate vigilant monitoring of pulsars, looking for sudden changes in timing or unexpected variations in emitted radiation. If these transformations are indeed occurring, they would suggest that nature accommodates forms of matter that are far more exotic than anything we have encountered in laboratories. The notion that a neutron star can shift from one extreme state to another adds a fascinating layer to our understanding of compact objects. Imagine the possibility of planets orbiting neutron stars, worlds that by all expectations should not exist. The discovery of planets around neutron stars has taken many by surprise, as the violent events that form these compact remnants typically obliterate or expel any nearby celestial bodies. Several pulsars host planets that orbit steadily, hinting at either remarkable survival or formation from debris following the original star's explosion. These planets face intense radiation and extreme gravitational forces, making them vastly different from typical worlds that circle ordinary stars. Some may have emerged from disks of material released during a supernova, while others could be remnants of companion stars that were disrupted. Their unusual origins prompt intriguing questions about how planets can form or endure in such hostile environments. By studying these celestial bodies, researchers can delve into the outer limits of planetary physics, examining worlds shaped by conditions that starkly contrast with those that influenced our own solar system. These peculiar planetary systems underscore the resilience and diversity of planetary formation across the cosmos. Additionally, neutron star collisions might produce unknown particles. When two neutron stars spiral together and ultimately merge, they create some of the most extreme conditions in the universe. Temperatures soar and densities increase, resulting in an environment where nuclear reactions and particle interactions reach energies far beyond what we can achieve in particle accelerators. Such collisions might generate particles that do not appear in ordinary reactions, unveiling aspects of physics that remain elusive under typical cosmic conditions. The mysteries of these phenomena invite you to reflect on the vastness of our universe and the incredible possibilities it holds. Gravitational waves and bursts of radiation emerge from these cosmic events, carrying subtle information about the particles involved. When unknown particles are created, they might influence the distribution of energy or alter the signatures that telescopes observe. Each merger presents a unique opportunity to explore matter at its most extreme, offering insights into the behavior of fundamental particles under conditions that existed only for a fleeting moment in the early universe. Some neutron stars spin in ways that challenge our current understanding of physics. While neutron stars are recognized for their rapid rotation, some exhibit spin rates or timing behaviors that defy theoretical expectations. Certain pulsars maintain remarkably stable periods, while others experience sudden glitches, causing unpredictable changes in their rotation speed. A few spin so quickly that their very survival seems to contradict the limits of structural integrity. These intriguing behaviors may stem from complex interactions among the crust, superfluid interior, and magnetic fields. They might also suggest processes that remain elusive, such as interactions with exotic matter or instabilities rooted in quantum phenomena. By observing these spin patterns, researchers can test models of how compact objects evolve and how their internal layers interact. As you reflect on these cosmic wonders, consider the mysteries still waiting to be uncovered. Would you like to continue exploring, or perhaps take a moment to rest? Neutron stars exhibit a fascinating diversity in their rotational behaviors, hinting at complex mechanisms that challenge our understanding of physics. You might consider that there are pulses of activity from these stars that remain undetected. They emit radiation across a broad spectrum of wavelengths, much of which is highly directional. If their beams do not intersect Earth, their signals go unnoticed. As a result, many neutron stars could be hidden from us, simply because their emissions don't align with our line of sight. Beyond their regular pulses, neutron stars have the potential to produce bursts, flares, or subtle vibrations. These phenomena may be too faint or brief for our current instruments to capture. It's possible that uncovering some of these emissions will require new detectors or more sensitive surveys. Entire classes of neutron star emissions might exist just beyond the reach of our existing technology. Detecting these hidden emissions could significantly enhance our understanding of how neutron stars transfer energy, how their magnetic fields evolve, and how their interiors respond to stress. The unexplored behaviors of these compact objects likely represent a rich and intriguing realm within astrophysics. Neutron stars may even hold vital clues about the universe's earliest moments. You find yourself drawn to the mysteries of neutron stars. These celestial bodies contain matter compressed to densities akin to those present shortly after the universe began. By studying them, you gain insights into physical conditions that no laboratory can replicate. Their cores may hold secrets about the interactions that shaped the early cosmos, including the transitions between different states of matter. As you explore their crusts, magnetic fields, and oscillations, you uncover reflections of fundamental forces that influenced cosmic evolution. Observations of neutron stars in binary mergers provide crucial data about how matter behaves under extreme temperatures and densities, reminiscent of conditions from the universe's earliest moments. By decoding the signals from these cosmic events, you hope to learn about the forces and particles that were at play in those first fleeting seconds. Neutron stars act as natural time capsules, preserving information from epochs that are otherwise beyond our reach. Some of these stars might even be on the brink of transformation into black holes. As neutron stars age or accumulate matter from their companions, they approach a critical threshold where gravity can overpower all internal pressure. When this limit is crossed, the star collapses into a black hole. As you reflect on these fascinating processes, you are invited to continue your exploration or take a moment to rest, pondering the wonders of the universe. This transformation does not happen suddenly. Instead, it unfolds gradually, marked by a series of internal changes as the star becomes more compact. During this process, shifts in rotation, magnetic fields, and emission properties can be observed. By studying these signs, astronomers may glimpse the stages leading up to a star's collapse. These transitions highlight the delicate balance between the stability of neutron matter and the gravitational forces that give rise to a black hole. Identifying stars on the verge of this transformation can offer profound insights into the fundamental limits of matter and the intricate pathways that lead to the formation of black holes. The crusts of neutron stars may harbor the strongest materials in the universe. The outer layers form a crystalline lattice of nuclei, tightly packed under extreme pressure. This unique material must endure colossal magnetic fields and withstand the immense stresses from rotation and internal motions. Calculations indicate that the structure of this crust could be hundreds of times stronger than any known substance on Earth. It has the ability to deform without breaking, endure significant strain, and store vast amounts of elastic energy. When this crust eventually gives way, it may result in sudden changes in rotation or bursts of radiation, marking a dramatic moment in the life of a star. Understanding the properties of this extraordinary material reveals how neutron stars respond to stress and why they sometimes undergo sudden changes. Their strength is a reflection of the unique conditions present in these compact objects, where extreme density and pressure give rise to forms of matter that cannot be found anywhere else. As you explore the cosmos, consider the mystery surrounding comets. They carry some of the oldest material in our solar system, yet their true origins remain a puzzle. While many scientists believe that comets originate from a distant reservoir known as the outer cloud, we have yet to observe this area directly. It lies so far from the sun that any objects within it reflect almost no light, rendering them effectively invisible to our telescopes. The few comets we do see are those that have been nudged inward by gravitational disturbances, but these represent only a tiny fraction of what likely exists. Their compositions vary significantly, hinting at different birthplaces and histories. Some comets contain ingredients indicative of deep cold environments, while others show signs of having been processed in warmer regions. This remarkable diversity suggests that comets may form in multiple zones or migrate long distances before settling into the distant reaches of the solar system. As you reflect on these cosmic wonders, consider the vastness of what remains to be discovered. The universe holds many secrets, waiting for curious minds like yours to unravel them. Imagine a time when our ability to uncover the mysteries of the universe expands. Until we find ways to detect objects across those vast distances, much of their origin will remain a hidden chapter in the story of our solar system. There may be entire clouds of objects that lie beyond the reach of our telescopes. Astronomers believe that the outskirts of planetary systems could harbor immense collections of icy bodies, far greater in number than the comets and asteroids we currently observe near the sun. These distant clouds might contain trillions of small objects silently drifting through the cosmos. Since they reflect so little light and are positioned at such great distances, even the most powerful telescopes struggle to detect them. Our understanding of their existence comes from observing the behavior of long-period comets and from theoretical models of planetary system formation. These unseen populations could include a variety of bodies, each with unique compositions, shapes, and histories, all shaped by conditions in the early solar nebula. They might even influence the motion of nearby stars, or bear witness to subtle gravitational interactions from ancient encounters. To detect these elusive objects, we will need future missions equipped to sense faint thermal signatures or gravitational effects across vast distances. Until that time arrives, the outermost regions of planetary systems will remain some of the least explored areas in astronomy. The space between stars may hold more than just dust and gas. Often described as a delicate blend of particles and radiation, interstellar space reveals a surprising complexity. Observations of absorption lines and faint emissions uncover unexpected molecules, unusual temperature gradients, and structures that defy simple explanations. Some areas seem to host dense clumps of material drifting independently, while others display magnetic patterns stretching over vast distances. You might also encounter charged particles and tiny grains with properties unlike those found in our solar system. These elements play a crucial role in how light travels through space, how stars accumulate material, and how shock waves from supernovae propagate. The interstellar medium is dynamic, continuously shaped by stellar winds, radiation, and passing clouds. To truly understand it, you must weave together insights from chemistry, plasma physics, and cosmic dust studies. Rather than being empty or straightforward, the space between stars could be a vibrant and evolving environment. Invisible structures may be moving through this vast expanse. As astronomers carefully map the galaxy, they discover variations in starlight that suggest the presence of objects or patterns passing between us and distant stars. Take a moment to reflect on the wonders of interstellar space. What mysteries might it still hold? You observe that certain features in space do not align with the behavior of known clouds or dust. Some of these phenomena appear to be transient, shifting in ways that are too rapid for ordinary interstellar material. Others exhibit effects that suggest large diffuse structures with properties distinctly different from typical gas or dust formations. Imagine these invisible shapes composed of extremely fine particles, magnetic filaments, or low-density materials that interact with light in unique ways. They might form naturally through turbulence or arise from processes that remain a mystery to us. Detecting these structures requires careful and repeated observations of the same stars, along with a meticulous analysis of subtle changes. If these enigmatic structures are indeed common, they could significantly influence how matter cycles through the galaxy, shaping star formation and the distribution of interstellar materials. Their elusive nature serves as a reminder of how much remains to be discovered in the vast expanses between stars. You also notice some rogue objects drifting through space that defy easy classification. Occasionally, astronomers identify these objects moving along trajectories that do not resemble those of typical comets, asteroids, or planets. These rogues wander freely, unbound to any star. Some may be fragments from disrupted planetary systems, while others could have formed independently in the cold, dark regions between stars. As you reflect on this, consider the mysteries still waiting to be unraveled in the universe. Would you like to explore more about these fascinating celestial phenomena or take a moment to ponder their significance. The properties of these celestial wanderers are incredibly diverse. Some exhibit comet-like behavior as they approach a star, while others resemble dense, rocky bodies. Their speeds hint at origins that are either distant or tumultuous. Since they don't linger in our solar system for long, studying them demands swift observation and meticulous analysis. These cosmic visitors provide valuable insights into the variety of materials present in the galaxy and the mechanisms that eject objects from planetary systems. Their unique characteristics challenge our existing classifications and suggest that the galaxy may harbor countless forms of wandering bodies that we have only just begun to discover. Interstellar space could be home to reservoirs of ancient, frozen material. In the cold regions far from stars, molecules and dust grains can remain unchanged for vast stretches of time. These reservoirs might contain frozen gases, complex organic compounds, and minerals that predate many stars in the galaxy. When such material is disturbed by shock waves or passing objects, fragments may drift into denser areas, playing a role in the formation of stars and planets. Some of this frozen material could even carry traces of the chemical processes that took place in the galaxy's earliest stages. Additionally, these reservoirs influence the temperature and ionization of interstellar clouds, shaping the cycle of matter between stars. Take a moment to reflect on the mysteries that lie beyond our solar system and consider how much more there is to explore and understand. Would you like to continue this journey, or perhaps pause and ponder for a while? Detecting these elusive entities proves challenging as they emit minimal radiation. However, faint signals in the infrared and radio frequencies offer subtle hints about their existence. These silent reservoirs of ancient material act as archives of cosmic history, preserving vital clues about the conditions that shaped the galaxy's earliest environments. You might imagine vast, complex magnetic fields stretching across immense distances. The galaxy is interwoven with these magnetic forces, twisting and bending as they interact with charged particles. Mapping them is no easy feat, as they do not emit light directly. Instead, they reveal their presence through the behavior of cosmic rays, the polarization of starlight, and the movement of gas clouds. In some areas, you can observe remarkably coherent structures extending through interstellar space, indicating large-scale organization. In contrast, other regions display chaotic patterns formed by turbulence or shock waves from exploding stars. These magnetic fields play a crucial role in influencing star formation, guiding charged particles, and regulating the temperature of interstellar gas. They may also define the boundaries between different regions of the galaxy, creating large, invisible frameworks that impact the movement of matter. Grasping the complexities of these magnetic structures is essential for modeling the behavior of the interstellar medium. As you reflect on this cosmic tapestry, consider how much remains to be discovered. Would you like to continue exploring, or perhaps take a moment to rest? Many details remain shrouded in mystery. Their complexity suggests processes that stretch across vast distances and unfold over immense spans of cosmic time. You might wonder if there are waves traversing space that we have yet to recognize. Beyond the gravitational waves that ripple through space-time, there could be other types of waves moving through our galaxy. These might stem from oscillations in magnetic fields, fluctuations in charged particle densities, or variations in interstellar pressure. Some of these waves may travel slowly through diffuse gas, while others could race across regions filled with plasma. Their elusive nature makes them challenging to detect with conventional instruments, as they do not emit strong light. yet their presence may significantly influence star formation, the behavior of cosmic rays, and the distribution of materials throughout the galaxy. To uncover these hidden waves, we would need sensitive measurements of radio emissions, polarization patterns, or minute changes in the motion of interstellar gas. Discovering such waves would unveil new pathways for energy flow in cosmic environments, enriching our understanding